Hello everyone, in today's video I'm talking about turbo derivatives, a real-time cross-asset pricing and risk library which was first developed in 2012. If you work at a hedge fund or a bank, keep watching. The library has been licensed to several financial institutions in both binary and source code form. The software runs in real time and never leaves the end user waiting for results. It runs on multiple CPU cores, can be used from Excel, Python and C++, and contains 450 plus cross-asset functions, including functions to fit curves and generate risk for portfolios of cash and derivative trades. To begin, we will start with a spreadsheet demonstration, but later we will show how we can price and risk portfolios using Python. This demonstration takes a closer look at the pricing and risk functionality the software provides and focuses on the accuracy and performance of the analytics engine behind the turbo derivatives software. Extensive focus has been put on developing a multi-threaded, performance-optimized risk engine which efficiently leverages all the cores on the CPU when generating risk. Every trade is valued individually and accurately with no approximations or mathematical shortcuts taken. This first worksheet demonstrates how few functions are actually needed to price and risk entire portfolios of trades. The cells in yellow highlight the just 4 key functions used to load, price and risk the portfolio. We show how quickly a curve can be built in a portfolio of 7,500 swaps, loaded and valued using the curve. We also demonstrate how quickly a delta ladder for the portfolio can be generated. Here we show the software curve being built. In this example, we build the curve from curve data embedded in the sheet, but the software allows you to load curves from files and to subscribe to curves published on a message bus. Next, we load the trades in the portfolio. In this example, we configured a portfolio of 7,500 interest rate swaps with maturities varying from 2 years to 30 years. The function quickly loads the trades in the portfolio by using multiple CPU cores. Once the portfolio is loaded, we call the tdport getPortfolioInfo function to return some basic details about the portfolio just loaded. The function returns a string flagging the portfolio contains 7,500 swaps and the memory used to store the portfolio is 21 megabytes. This PC has 32 gigabytes of memory, so the swap portfolio is using less than 0.1% of available memory. With modern-day motherboards supporting up to 256 gigabytes of memory, there's really no limit to the number of trades you can have in any given portfolio. We have run load tests using as many as 1 million trades. Once the trades are loaded, we value the portfolio using the function tdport generate MPV. We output the results to an in-memory table which we display here. The portfolio values instantly and the 7,500 rows of trade detail can quickly be displayed. We then call the function tdport generate delta matrix to generate the delta ladders for every trade in the portfolio. This function bumps every point on the software curve up and down by half a basis point, refits the curves and revalues all 7,500 swaps to generate the delta ladder. This effectively involves valuing 480,000 swaps to generate the delta ladder for the full portfolio. The function quickly generates the ladders for all trades in the portfolio in just a few milliseconds. On the next worksheet, we demonstrate how easy it is to pull back the covers of the engine and see the details behind the calculations. We can pick any swap in the portfolio and see all the cash flows behind the swap, including accrual dates, pay dates, forward rates, and the discount factors used to discount cash flows. In this case, the swap chosen is a fixed versus floating swap, so you can see the cash flows for the fixed leg of the swap in blue on the left-hand side of the screen, and the cash flows for the floating leg of the swap in yellow on the right-hand side of the screen. On the next worksheet, we generate a set of gamma ladders for the swap portfolio. Gamma ladders show the impact of a 1 basis point change to each point on a set of shifted yield curves. We will generate 8 sets of shifted curves with shifts from minus 50 basis points to plus 50 basis points. We will then generate a delta ladder for the swap portfolio for each of those shifted curves. We have 7,500 swaps in the portfolio and 9 shifted curves with 32 tenors on each curve. Generating a single delta ladder requires shifting each tenor point on the shifted curve up and down half a basis point, refitting the curve, and using the fitted yield curve to revalue the swap portfolio. Generating the delta ladders for all 9 shifted curves involves just over 4.3 million swap valuations. The TD port generate delta matrix function was used in the previous example, but this time the function sees it's being passed multiple curves and it generates the ladders for each shifted curve in the one call. It takes just under a second to complete. All the ladders are output to an in-memory table, which is then rendered to the spreadsheet surface. In this example, we will quickly show how the library can be used to create a market monitor showing grids of spot and forward starting swap rates. The first grid is a grid of live rates, the second grid is a grid of closing swap rates for the prior day, and the last grid is a grid of swap rate changes on the day in basis points. We can use the TD swap index rate function to calculate the swap rate for a given start and end date. Tenors or dates can be passed as arguments to the function. When we call the function, we can see a single swap rate for a spot starting 1 year swap is returned. If we call the exact same function but instead pass in arrays of start tenors and end tenors, the one function call will return swap rates for a full range of swap start and end dates. We can use this approach to generate another grid of closing spot and forward starting swap rates, and then use an Excel lambda map function to display a grid of changes on the day. In this final demonstration, we will go through all the steps we took to create the spreadsheet market monitor page, but this time use Python to create the market monitor. Let's step through the program line by line. All the output from the program will be displayed in the console window at the base of the page. The first thing the program does is to import the turbo derivatives library and initialize the library so that we can call all the turbo derivatives functions from Python. We then import the two curve sets for the live curve and the closing curve for the prior day. The next thing we do is set up the tenors for all the swaps that we want to calculate the swap rates for. So we define the start tenors of all those swaps, we define the maturity tenors of all those swaps, and then we call the swap index rate function to calculate the swap rates for the whole range of spot and forward starting swaps. We then display those live swap rates and then move on to looking at the closing swap rates. So again, we call the swap index rate function, but this time to calculate the grid of closing swap rates from the prior day. And then the last step was to actually display a grid of the differences between the two sets of swap rates. And that we did using a lambda function, which we can achieve using Python code as well. So here we evaluate the lambda and we pass in to the map function the live swap rate array and the closing swap rate array, and the differences are returned and displayed. Just to show how we can also use Python to call into the risk functions in the library as well, I've called a couple of the functions to actually generate delta ladders and risk using the turbo derivatives library. So here again we import the portfolio we were using in the spreadsheet examples. That portfolio consists of 7,500 swaps. We import those swaps and then we generate a delta ladder for the entire portfolio by calling the generate delta matrix function, and finally we print out that delta ladder.